Good afternoon, good morning, and good evening, everybody. My name is Zixuan, and I'm a PhD student from the University of Bristol. I'm going to present some of our recent work about imprecise belief fusion in collective learning. I'll first introduce the framework of collective learning and then the belief fusion operators, both for fusing with other agents and fusing with evidence from the environment. I'll also talk about the simulation setup and some key results by presenting some figures to you. So firstly, let me introduce the collective learning framework we started. Collective learning is kind of task where a system of agents attempts to learn something. Here, the thing is the true state of the world. The learning process is formed up with two information sources, indirect evidence from other agents and the direct evidence from the environment. Ideally, the system will be able to reach a global consensus over time. One possible application is the search and rescue task. Another one is wildfire monitoring. On the figure at the right-hand side, the orange squares could be the locations of resources, casualties, or something else, and the gray squares are just nothing. And the team of blue agents will be searching the environment and communicate with each other to make a collective decision on where the target positions are. We model such scenario this way. The environment can be described by a finite set of propositions P1 to Pn. Then a state will be the allocation of Boolean choose values to each of the propositions. So a state is a complete map of where all the charities are. In the figure, each square is a proposition, and a state would be the complete description of the grid. More specifically, we can allocate orange squares are true or 1, and the gray squares are false or 0 to represent if a square has charities or resources or not. So in other words, the orange squares would have something we want, and the gray squares wouldn't. A belief B is then represented by a set of states, and here we let S denote the set of all possible states. So B will be a subset of S, and all agents starts from a belief of ignorance in our simulation. In other words, the initial belief B is equal to S. Then I'd like to introduce something about how the agents learn from both direct and indirect evidence. Let's go for the direct evidence first. If an agent is uncertain about some propositions, then it will investigate one of them at random. Then, with a probability of rho, it receives some evidence about the value of proposition I, which is the proposition she visited. Also, there's another probability of epsilon, with which the agent receives the incorrect value of pi. We call this epsilon the error rate. Once receiving the evidence, the agent updates their belief this way by the equation at the bottom here. For example, if the blue agent receives the evidence of P3 is orange, then it will replace all the P3s in each state of its belief set with orange, which is the value she received, like this, so that it achieves updating the belief and learning from the evidence from the environment. And got a new belief here. So also in order to propagate the information through the system, agents will fuse their belief by a similarity-based operator. The similarity being used here is the Jekyll similarity, which is a cardinality of intersection of two sets over the cardinality of union of them. If the similarity between two beliefs is higher than some threshold, then we take the intersection of two beliefs as a fused belief. Otherwise, we'll take the union. For example, have a look at the blue and green agent over the top right. Their belief has a similarity of 1/3. So if the similarity if the similarity threshold gamma is less than 1/3, the fusion result will be like this, the intersection of the two beliefs. On the other hand, if gamma is greater than or equal to 1/3, the fusion result will be the union of them. Please note that when gamma is equal to 0, the operator will be equivalent to the well-known dubious and Perot operator, which was proposed in a paper in 1988. So the next question will be, how do we set up our simulation? If we have an agent like the blue one on the top, who is uncertain about some propositions, the agent will randomly select an uncertain proposition to investigate. The blue one here will choose P3 as it is the only one she's uncertain about. But if for some agent there are two uncertain propositions, either of them will get the probability of 0.5 to be investigated. So for 3 uncertain propositions, there will be a probability of 1/3 for each of them. So that will be distributed evenly. So after investigation, the agent might get some evidence or not, which is dependent on the evidence rate rho. After collecting evidence, the agent will then attempt to fuse her belief with somebody else. Again, she might succeed or not, depending on another parameter of fusion rate, which is sigma. For these two actions, if she succeeds in either, she will update her belief using corresponding method we described on the previous slides. Otherwise, she will just simply keep her current belief. After these two actions, she will then go for the next iteration from the start again. So to summarize, each agent will take two actions in each iteration, which are uncertain proposition investigation and fusion attempts. But if the agent is certain on all the propositions, like the green one, who holds a singleton belief, she will skip the evidential updating and go for a fusion right way. So, based on this simulation setup, we've run some experiments. Let me present the most interesting results to you. We studied the impact of imprecise level of the fusion operator on the performance of the system's convergence. More specifically, we varied the threshold gamma of the Jacob operator, which represents the degree of imprecision of the fusion. We will use mainly two measures to evaluate the system: the proportion of propositions that are correctly determined by the population, which is alpha, and the F3 score, which is to balance getting the right answer against being uncertain rather than getting the wrong answer. This is because that in noisy environment, it is sometimes better to be uncertain than to be incorrect. In order to calculate that score, we use theta for the proportion of propositions that are not incorrectly determined. In other words, it is the sum of correct and uncertain propositions. And then the F3 score can be got by the by the equation where we can replace beta with 3. The equation is at the bottom. On the figure, F3 score and alpha and the proportion of determined proposition are plotted. The proportion of determined proposition is calculated by alpha plus 1 minus beta. We can see from the figure, the optimal performance can be got at around 0.4 if we care more about F3, and at around 0.3 if we care more about alpha, which is here and here. So despite which measure we choose, the system convergence can be improved by increase the imprecision of the fusion process compared with the standard dubious and proud operator, which is when gamma equal to 0. We then varied the fusion and evidence rate to study how that will impact on the optimal level of imprecision of the fusion process. The figure is for optimal thresholds gamma on both alpha and F3 for the left and right respectively. The top left corners on both figures are red, but the rest are dark. So we can see that an imprecise operator is optimal if the evidence rate is relatively low compared to the fusion rate. Also, the general pattern is the higher the frequency of the fusion compared to the frequency of the evidence, the more imprecise the operator should be to get the system better performance in the context of alpha and F3. We also did the same to the error rate. From low noise to high noise, the optimal threshold for F3 goes up a bit, the optimal threshold for alpha goes down a bit, but it is generally much less affected by the change of noise level. So, to conclude, we suggest the following. If sigma is high relatively to rho, which is the fusion rate and the evidence rate, then optimal results are obtained by a more imprecise operator. And the optimal level of imprecision is strongly dependent on the frequency of evidence relative to the frequency of the fusion, which is rho to sigma. And it is much less clearly dependent on the level of evidential noise epsilon. Furthermore, in the paper, we also found the system performance is affected by the relative relationship between the evidence rate rho and the fusion rate sigma. I didn't present rho's result because of the time limits. You can refer to the paper if you are interested. And following this work, there are some potential future directions. One is about other imprecise fusion operators based on alternative measures of similarity or distance. For example, we can apply a threshold operator based on Hamming distance. Also, we have seen that preserving a imprecision during belief fusion leads to a better performance in the context of collective learning. We seek to explore whether the imprecise forms of evidential updating may lead to similar improvements in the learning process. Finally, we also want to do some simulated robot experiments, and it will help us to investigate a more grounded collective learning scenario in which to better understand the implications of our model when external constraints are imposed by the robot hardware, such as the communication bandwidth limits and the noise from the onboard sensors of the robots. And that's it. Thanks for your attention. Feel free to ask me any questions. Thank you.